On July 1st, 2025, when the 3E Atlas was discovered, NASA's first size estimate was cautious. They said the nucleus was somewhere between 440 meters and 5.6 kilometers across a range so broad it was nearly meaningless. Nobody knew for sure, not at first, but soon, as the post-perihelion data from the Hubble Space Telescope began to come in from December 2025 through January 2026, everything began to change. For the first time, astronomers were able to carefully subtract the coma's bright glow surrounding the nucleus and see the solid core directly. The measurements settled at a precise 2.6 kilometers in diameter, with an uncertainty of plus 0.4 kilometers. This was significant. To put it into perspective, 2.6 kilometers is roughly the length of the distance between Big Ben and Tower Bridge along the south bank of the Thames, or the width of Retiro Park in Madrid. This is the size of an object that has been traveling through interstellar space for 7 billion years, and it passed through our solar system for the past 8 months. Avi Loeb, an astrophysicist, immediately began calculating the implications of this size. Since mass scales as the cube of the diameter, this meant that 3 Atlas was about 40 times more massive than 2I Borisov, a comet discovered in 2019 with a nucleus around 0.7 kilometers in size. This also made 3 Atlas at least 20,000 times more massive than Oumuamua, the mysterious interstellar object discovered in 2017, whose length was under 200 meters. These differences weren't just incremental, they were orders of magnitude. But physical size was only the beginning. A 2.6 kilometer nucleus implies a population density of interstellar objects in our galaxy that could dramatically change the way we view space. This discovery suggests something important about the early history of our solar system that most people haven't heard about. It points to a chemistry of life that is still being processed by scientists worldwide. Philosophically, if you follow this logic to its end, it implies something profound about our place in the universe. A universe that seems to constantly seed its planetary systems with ancient chemicals from dying stars. Whether we notice it or not, today we are going to build this story from the solid measurement of size outward, starting from the nucleus of 3 Atlas and moving all the way to the broader galaxy. Stay with me as we dive into the details. Let's look at the size debate first. The journey from the first estimate to the final number is an important one because it reveals something crucial about how difficult it is to measure an interstellar object, the core challenge, the coma. An active comet is surrounded by a cloud of gas and dust, called a coma, that can extend hundreds of thousands of kilometers away from the nucleus. The nucleus itself, by comparison, is tiny. When you image the comet, you mainly see the bright coma with the nucleus buried inside it. To measure the size of the nucleus accurately, astronomers need to subtract the coma's light precisely to isolate the faint point source of the solid core beneath. In July and August 2025, Hubble imaged 3E Atlas in its pre-perihelion phase. At this point, the coma was bright and extended, and the nucleus couldn't be directly resolved. A team led by David Jwitt could only establish limits. They suggested the nucleus was somewhere between 440 meters and 5.6 kilometers, based on indirect measurements. The lower limit came from the minimum size needed to sustain the observed outgassing rate, while the upper limit was based on an assumption about the comet's albedo or reflectivity. The range of uncertainty was significant, so the precise size remained unknown for some time. The situation didn't improve until 3 Atlas passed perihelion on October 29, 2025. The comet passed behind the Sun, causing telescopes to go blind for a while. However, when the comet re-emerged in late November and December, the coma had changed. The intense solar heating at perihelion had depleted the near-surface CO2 layer, and by the time it passed through the inner solar system, the coma was now less dominated by CO2 and more by the deeper CO reservoir. The coma had a different structure now, and critically, it had become slightly less bright compared to the nucleus. Manuhoy and colleagues obtained new Hubble images from December 2025 through January 2026. They applied a technique called point spread function subtraction, which carefully models and removes the expected coma light distribution, leaving only the residual central point source that represented the nucleus. This method finally allowed for the detection of the nucleus across multiple observational visits, and the result was clear. The effective diameter of 3 Atlas's nucleus was found to be 2.6 kilometers, with an uncertainty range of plus or minus 0.4 kilometers, assuming a typical cometary albedo of 0.04. This was the first time astronomers had a solid, reliable measurement of the comet's size. A second independent method, which involved fitting non-gravitational acceleration models to the observed outgassing rate and nucleus density, confirmed the 6-kilometer figure. Both methods led to consistent results, further narrowing down the size estimate. Despite this, some sources still mention a range between 2 and 8 kilometers due to remaining uncertainties in albedo, the reflectivity of the object's surface. If 3 Atlas has an unusually high reflectivity, its nucleus could be smaller, while a darker surface could make it larger. However, the most probable size, consistent with both direct detection and dynamic constraints, is 2.6 kilometers. This 6-kilometer nucleus is significant in comparison to other interstellar objects. To understand its importance, we must compare it with 2 previous interstellar visitors, Oumuamua and Borisov. Oumuamua, discovered in 2017, had a length estimated at under 200 meters with no visible coma and no detectable outgassing. Despite this, it exhibited strange behavior, including non-gravitational acceleration, which still hasn't been fully explained. Then there was Borisov, discovered in 2019, whose nucleus measured about 0.7 kilometers. It was a true comet, displaying typical behavior with a coma and outgassing water and carbon monoxide. But unlike Oumuamua, it behaved more like a typical solar system comet. Now, 3 Atlas, with its 6-kilometer nucleus, stands out. According to Loeb's calculations, 3 Atlas is 40 times more massive than Borisov, and more than 20,000 times more massive than Oumuamua. This makes 3 Atlas the most massive interstellar object ever detected passing through our solar system. But why does this matter? First, a more massive object like 3 Atlas carries more material, more chemistry, and more of whatever it is made of. The molecular inventory detected by telescopes like ALMA, Webb, SWIFT, and Spherex methanol at 4 times the solar average, HCN, methane, and nickel was released from a 6-kilometer nucleus, not a 200-meter sliver. The larger the nucleus, the larger the reservoir of material available for release during its passage through the solar system. Second, a more massive object is harder to detect from a distance. Had 3 Atlas been the size of Borisov, 0.7 kilometers, it would have been about 14 times fainter when first discovered. If its nucleus were only 440 meters, it would have been practically invisible at the distance where 3 Atlas was found. This means that for every 3 Atlas we detect, there are likely many smaller interstellar objects passing through our solar system undetected. But third, and most importantly, The size distribution of interstellar objects has significant implications for how many similar objects exist in our galaxy. The fact that 3 Atlas is the largest interstellar object we've detected, yet it's far from the largest size possible, tells us a lot about the population of such objects. This brings us to the population implications of 3 Atlas. How many of these objects are out there in the galaxy right now? This is where the size measurement becomes truly significant in a cosmological context. Stay with me through the logic, because the conclusion is genuinely surprising. When astronomers detect an object in a survey, they can estimate the total population of similar objects by correcting for the survey's sensitivity and sky coverage. The detection of 3 Atlas by the Atlas survey in July 2025, combined with the survey parameters and the object's brightness, allowed an estimate of how many similarly sized interstellar objects exist within our solar neighborhood. Manuhoy and colleagues, in the same paper that reported the 6-kilometer nucleus measurement, calculated a lower limit. According to their calculations, there is at least one 3 Atlas-sized interstellar object within 4.5 AU of the Sun, which is within the orbit of Jupiter. In other words, right now, at this very moment, there is likely an object of at least 2 kilometers across from another planetary system, probably around 7 billion years old, passing through our solar system. We just can't see it yet. Maybe it hasn't gotten close enough to become active and visible, or maybe it's approaching from a direction that our current surveys haven't covered. Alternatively, it might have a lower albedo, reflectivity, than 3 Atlas, making it harder to detect. It could also be passing through a region of space that doesn't allow it to be easily detected. The paper notes that this lower limit is likely conservative, meaning that there could be even more of these interstellar objects out there than we are currently detecting. The situation is made more complicated by the fact that inactive interstellar objects, like the rocky Oumuamua type, are much harder to spot. These objects don't brighten near the Sun, they don't develop tails, and they remain dark as they speed through space. At the distances where 3 Atlas was discovered, we would almost certainly miss them, as they would not be visible to current telescopes. Looking ahead, the Vera C. Rubin Observatory, which is now operational, will dramatically increase the rate at which we detect interstellar objects. The observatory's LSST, Legacy Survey of Space and Time, covers the entire accessible sky every few nights and goes much deeper than the Atlas survey. Projections suggest that Rubin could detect multiple interstellar objects per year, whereas previous surveys, like those that discovered Oumuamua, Borisov, and 3 Atlas, detected 1 per decade. Each new detection will add a data point to our understanding of the size distribution of interstellar objects. With enough detections, we will begin to understand how the interstellar object population is structured, how many large ones versus small ones there are, how their chemistry varies, and how their size distribution compares to the distribution of objects ejected from planetary systems during formation. 3 Atlas, at 2.6 kilometers, is not just another interstellar object. It serves as a calibration point for the entire census of interstellar material flowing through the galaxy. It offers an opportunity to better understand the size and chemical makeup of objects from other stellar systems. The more we learn, the clearer it becomes that this data will change our understanding of the interstellar medium and our solar system's place in the galaxy. But the implications of 3 Atlas extend far beyond its size and population. Let's now connect its physical size to the chemical detections made during its passage through our solar system, because the size of the object tells us something important about how to interpret the molecular abundance measurements we've made. When ALMA, Atacama Large Millimeter Array, detected methanol at 8% of the total vapor in 3 Atlas's coma. It was 4 times the solar system's average. This measurement was made from the coma, which is the gas released from the surface of the nucleus. The 8% methanol figure tells us about the composition of the surface volatiles, essentially the outermost layer of the nucleus that was exposed to solar heating during its approach. But the nucleus of 3 Atlas is 2.6 kilometers across, which means that the surface is only a small fraction of the total volume of the object. The post-perihelion eruption documented by Spherex in December 2025 exposed deeper layers of the nucleus. These deeper layers had not been heated by the sun since 3 Atlas formed in its protoplanetary disk, possibly 7 billion years ago. This means that the chemical composition of the interior may differ significantly from that of the surface. The deeper material, revealed by the December eruption, might be richer in hypervolatiles like methane and carbon monoxide and could contain a different organic inventory than the surface material. The full chemical profile of 3 Atlas, therefore, is not just the 8% methanol figure that we observed on the surface. It is likely much more complex, with different molecular abundances found deeper within its 2.6 kilometer nucleus. These deeper layers may contain the prebiotic chemistry that was preserved for billions of years, untouched by solar radiation until now. This means that the object may hold clues to the origins of life, not just for Earth, but potentially for other planets across the galaxy. The interior chemistry, which we glimpsed in December, may hold the key to understanding how life could have arisen on Earth. These are the same kinds of chemical processes that could have been taking place in the early solar system when comets and asteroids bombarded Earth, bringing essential building blocks for life. 3 Atlas may have delivered some of that ancient chemistry, which could have been part of the prebiotic cocktail that led to the origin of life here on Earth. What we're seeing with 3 Atlas is more than just a comet passing through our solar system. It's a relic from another stellar system, one that formed in a cold, carbon-rich environment. The chemistry it carries with it is unlike anything we see in our solar system, and it may have played a role in the development of life on Earth billions of years ago. Now, let's take a step back from the specific measurements of 3 Atlas and think about what this object represents on a larger scale. While we've been discussing its anomalies, its CO2 to water ratio, methanol enrichment, strange jets, and sideways push, there's a risk of focusing too narrowly on the exceptional characteristics of 3 Atlas. We might miss something even more significant. 3 Atlas is, at its core, just a comet. It has a nucleus made of ice and rock. As it approaches the sun, it sublimes, producing a coma, jets, and a tail. Its chemistry is indeed unusual by solar system standards, but it follows the same basic principles we expect from objects formed in different environments. The fact that it follows a hyperbolic trajectory is entirely predictable. It's not gravitationally bound to the sunday. This is expected behavior for an object that originated in another stellar system and drifted through interstellar space for billions of years before passing through ours. The universe creates comets around every star, in every planetary system, across a wide range of environments, hot or cold, metal-rich or metal-poor, young or old. The comets that form in colder environments are enriched in CO2 and methanol. The ones that form in older environments show older isotopic fingerprints. The ones that travel for 7 billion years are faster, more irradiated, and more altered on their surfaces. So, 3 Atlas isn't an anomaly in the strictest sense. It's a textbook example of what happens when a comet forms around a star in a different planetary system, then drifts through space for eons before passing through ours. This is not a freak event, it's part of a much larger process that happens everywhere in the galaxy. The significance of 3E Atlas, then, lies not just in the specifics of its composition or behavior, but in what its existence implies about the connectedness of planetary systems. Our solar system is not isolated. It continuously receives material from other systems, and this cosmic exchange has been happening over geological time scales. The chemistry that 3 Atlas brought with it, the same methanol, HCN, methane, and other organic compounds, has been traveling through space for 7 billion years. It predates the Earth. It predates our Sunday. In a real sense, 3 Atlas is a message from the early universe, a remnant from a time when the Milky Way formed stars and planets in a different way than it does today. And yet, the story doesn't end here. While 3 Atlas has provided us with incredible scientific insights, it also highlights a missed opportunity. The size and complexity of this object revealed something about our scientific infrastructure, something that we weren't fully prepared for. We had the telescopes, Hubble, Webb, ALMA, SWIFT, SPHEREX, and they performed remarkably well, capturing critical molecular detections, measuring the nucleus, and analyzing the comet's jet morphology. These are real triumphs of modern science. However, we did not have a spacecraft that could get close to 3 Atlas. The Juno mission, which was already in orbit around Jupiter, had the potential to intercept 3 Atlas in March 2026. A proposal by Lowe, Hibbert, and Kra had suggested a 2.675 million kilometer maneuver to reach the object, but it wasn't executed. We observed the most massive interstellar object ever detected, but from hundreds of millions of kilometers away, instead of using a spacecraft that was already positioned within 27 million kilometers. The Comet Interceptor mission, which has been waiting at the L2 Lagrange point since 2024, was designed exactly for this type of scenario, but it was not in the right position to intercept 3 Atlas, and while the mission will be ready for the next interstellar visitor, that's only if the object is discovered early enough and comes from a direction that allows for an intercept trajectory. The deeper issue lies in the institutional response. When 3 Atlas was discovered in July 2025, the astronomical community immediately recognized its interstellar origin and began mobilizing observational campaigns. But to mobilize a spacecraft response, whether redirecting Juno or launching a dedicated interceptor, requires a decision-making process that operates on timescales of months. By the time the feasibility study for Juno was published, the maneuver window had already closed. This situation exposes a critical gap in our infrastructure. We need pre-authorized protocols for redirecting existing spacecraft to intercept interstellar objects. These protocols should be automatically triggered upon confirmation of an object's interstellar origin. Unfortunately, we don't have these protocols in place yet. 3 Atlas showed us both the incredible scientific potential of such objects and the operational challenges we face in responding to them. As we look ahead, we must be prepared to act faster with pre-authorized plans so that we don't miss the next opportunity to study these incredible visitors from other star systems. On March 16th, 3 Atlas will pass Jupiter and then it will be gone. But the data, the questions, and the implications remain. The implications about the size of the interstellar population, about the portability of prebiotic chemistry, and about what our solar system has been receiving from the rest of the galaxy are just beginning to be understood. So, what do you think? How does the 2.6 kilometer size of 3 Atlas change your perspective on this object? Share your thoughts with me in the comments below, and don't forget to subscribe to follow the latest updates as the Jupiter flyby data comes in. This is far from just a comet passing through our solar system. It's a message, a cosmic communication that we're still trying to understand. Stay tuned, because we're only beginning to read it.